Welcome back to ECE 220, day before the exam, and we'll try to spread out on the exam, and you will have bubble sheets. Hopefully it will be clear how to fill those out or complete those, and the back side of your bubble sheet is where you will fill in your answers for your particular problems. And the exam should be structured just like some of the practice exams. Hopefully it will not take you by surprise when you receive the exam and the bubble sheet to fill in. That's tomorrow, and you will have an hour to finish that exam. You'll have from 9:30 to 10:30. Plan accordingly. If you still have your lab to do this week, don't forget your data sheet. You'll need to bring in that data sheet because your TA actually initials as you work through each of the different parts, and as you record data, then you'll sort of be allowed to continue with the TA initials at the appropriate time on those parts. So bring your data sheet. That should be embedded in the instructions for pre-lab and lab. And I would recommend that you read through the lab so that you're not completely, you've done the pre-lab and the lab follows that, but I would go ahead and read through the lab and make sure you are pretty clear on what's happening with respect to the lab. Group B still has yet to turn in their pre-lab for Lab 1. That's Saturday. Next week, the Group A people actually have a couple of things to do. You need to turn in your report on Wednesday in the Dropbox, but then you'll have another pre-lab to complete by that Saturday. I haven't included that here, but I will maybe after the exam. I'm thinking you're focused right now on the exam, which is tomorrow. Today what we will do is actually split some sources. We have the right tools. We can hit it just right, and we can split these voltage sources and current sources. We'll work through a couple of examples illustrating that concept. Voltage sources, we now just put a couple of those in parallel with each other, and that allows us to piece them or split them up. A current source, we now combine those in series, and that allows us to pull apart a circuit and make the structure maybe a little cleaner. That's the idea behind this. These are tools to try to help us solve circuit problems. And then we'll put the source transformations and the source splitting together in an example, and if we have time, we'll get really complex at the end. I want to start talking about complex numbers because all of this material that we've been working through, we will be using complex numbers to do the same things at the end of the semester. We'll be analyzing circuits where instead of having resistors per se, we will have complex impedances. You can think of them like resistors, but now they are complex numbers corresponding to inductors and capacitors, and that will allow us to analyze sinusoidal circuit or circuits that are excited with sinusoidal waveforms instead of just constant waveforms. But when we go sinusoidal, then we'll have to move into complex numbers to make the algebra go transition from DC to sinusoids. That's where we are headed. I should have maybe provided a little bit more with complex numbers before now, but I think we'll be okay. We'll see how far we get today. Source splitting. This is the idea. Here we have a current source, and that current source is going to supply current I in that particular branch, which means, well, we could just have two sources that supply the same current in that branch, and that branch will still have a current of I through it. We haven't changed anything other than introduced a new source. We've split one into two that look exactly the same. Let's see how that plays out via an example. Here's the example that we will use to illustrate source splitting, and in particular, this particular example is going to split a current source, and the current source, that the only one that's in this example, is actually connecting the left and right hand sides of the network below. We have this interconnection, and it involves three meshes if we wanted to analyze it directly with what we can do, which is mesh current analysis. We could analyze it with node voltage analysis, but for me it looks like it's screaming to be analyzed by mesh current analysis. But let's do it another way. Let's analyze this circuit, try to collapse it into something that is even more straightforward from what it is right now. We have two voltage sources, and we have this current source up top that is connecting two different locations or two nodes in the circuit, in the sub-circuit below. If we split the current source using this idea, then that means that we need to put two dependent sources that look exactly the same in this redrawn or resketched version of the original circuit, where now we have the same current, and it depends on, so this is a dependent current source, but this is really all that we've done. I'm not necessarily going to relabel all the other pieces, but everything else is relabeled as it was in the original circuit. What I want to emphasize at this stage is the fact that I've now split that current source into two identical sources. And you're going, well, why'd you just introduce another source if it's the same? What I want to talk about now is look at what happens right here. Let's call that node A. If I now performed KCL at that node, do you see that I have 45I0 coming in and 45I0 going out? And that's what that dependent source is going to produce or yield. What would happen if I did that? Did I just mess everything up? Or what actually happened? Can I do this? Is this okay? Let's do KCL now at A. And what do I want to, let me call this I down. I guess I should have drawn a bear there and had bear down, but it's I down. I sub D, current going down, KCL at A says what? Well, we have 45 I sub 0 into the node A, and going out I sub D and 45 I sub 0. And those dependent sources are going to yield or always provide 45 I sub 0 in their branch. What does that imply about I sub D? So if that's 0, is it okay if I just put a wire there if no current's flowing? I'm not changing anything, am I? That's now going to allow us to split what's going on in the top half of that circuit. Meaning, do you see now that I can, well, let me draw it. Now what I want to do is emphasize, or actually I wanted it to go there and there. Because I have a dependent source, I can't change, or I don't want to disrupt. I need to preserve this, and that's not I down. That was I sub 0. Here was, what, 2 and 1, and this is a source, and this was a source. And I think that was 4 and 3. Are we okay with what I've done now? I had a wire down to that node between the 1 and 2 ohm resistor, and we were okay with that. Now I've just said, well, let me put another wire in there to be this similar to the single wire. Now I have both wires directly down to that node. I haven't changed anything, so now what I've done is redrawn this after splitting the source and introducing that connection between node A and in between the horizontal resistors of 1 and 2. Now I've drawn this, and what I'm hoping is after all of this time that we've played with these different source representations, you start to see a source in this mix, or two sources that might look something like we could transform into their equivalent. What do you see relative to these current sources? Is that a Norton equivalent or a Thevenin equivalent? If I just looked at, let's say, the left one that I've now highlighted in red. It's a current source in parallel with a resistor. That's a Norton, as is this one. I've now created two Nortons, but do you see if I could replace that parallel source with a series source, I would now have a series source in series with that 1 ohm resistor and another series source in series with that 2 ohm resistor. Meaning, let me now convert these Nortons to Thevenin equivalents. Well, let me just say Thevenin sources. How do I do that? Now I just worry about that node and that node on the left and replace that parallel source with its Thevenin source, the Norton source with the Thevenin, which means now if I maybe to make it look a little bit more like what you're used to seeing, And how do I now convert this into this? That's what I've done. What's the resistor value going to be? It's 1, isn't it? It's this resistor. What's this dependent source? It's 45 I sub 0 times R, which is 1. So this is now 45 I sub 0. And I have the other pieces of this circuit. Here's 4, here's 20. And now what do I have on the other side? If I replace this one, the Norton source on the right, with its Thevenin source, hopefully now you see that that looks like this. I'm going to break it off a little bit, but emphasize that it's there. What's the resistor value? It's 2. And what's the value of the source, dependent source? Isn't it IR? So that's now 45 I sub 0 times 2, or that's now 90 I sub 0. And you're going that. But if we redraw that just a little bit, let's now collapse some of those wires. And do you see now that I just have a mesh on the left and a mesh on the right? 2 meshes with some independent sources and dependent sources. I now can redraw this and say, oh, in fact, here's what I have on the left. And this was actually 25 ohms to begin with. And on the right, and that's now my equivalent circuit that I was able to produce by splitting sources. This now, maybe you think this looks a little easier to analyze than that. What did we do? We split the current source into 2, and that ended up yielding now these 2 meshes instead of a 3-mesh problem. And our dependent current source has now been split and ended up as 2 dependent voltage sources. But you could now analyze this relative to what you're given versus the original circuit, which involves that dependent variable I sub 0. Pardon? And so we've now illustrated source splitting with current sources. Let's look at source splitting with a voltage source. Here, let's say this is, go ahead and label these. Maybe this is now R sub B, R1, so we can sort of track what we're doing. Whoops, let me make sure I'm consistent with my notes. We now have this circuit. And we want to now split the voltage source. The reason we're splitting the voltage source is, or why we can, is because we're playing on the fact that that location or that node is always going to be at V. V is going to be inserted into the R1 and everything to the right, and it's also going to be inserted into that R sub B. That's sort of a bridge resistor bridging two sides of the circuit. What happens now if I split that voltage source into two voltage sources, maintaining the voltage V at that node? I'm now going to pull that node apart and have one of the parts be supplied by V and have the other part also supplied by V. Meaning, here is the sort of the interior piece. But now what I want to do is I said, well, let me pull off that same node and I now can redraw that circuit with two voltage sources. I've now split the voltage source, and that particular node, which I had isolated before or identified before, which was there and there, I'm maintaining the voltage V at that point. But now I've structurally changed this circuit to hopefully maybe allow me to analyze it a little bit more cleanly, because maybe what I want to do is change up the value on R sub L occasionally, and I would prefer not to have to keep dealing with R1, R2, R3, and R sub B in the voltages, and have some numbers over here replacing what's happening between those two nodes with something a little more simple. Which is what I'm wanting you to maybe see is if this and this were simplified down to a parallel combination, those two pieces would be in parallel. And then I could combine them and then get a Thevenin. But that's going to take me a couple of steps. Can I now take this blue highlighted piece and convert that into a Norton? And then I'll be able to collapse the R1 and R3 together or combine those and simplify that a little bit. So let's now convert these Thevenin sources to Norton sources. So let me say convert Thevenin sources to Norton sources. Meaning over here, what do I have? And that was connected over here. Whoops, I keep relabeling these. Which ones am I doing? R2 and R3. How do I label these current sources. What's the value of the current source on the left? If I'm now collapsing this Thevenin into a Norton. That's V over R, where V is V and R is R sub B. On the left then, down here I have V over R sub B. What do I have in this lower blue highlighted Thevenin if I want to convert that to a Norton? R1 is now going to be my resistance, and here I have V over R1. What's the next step that I want to do? Probably want to combine those two. I can now combine those resistors in parallel. And let me just not carry all of that forward. Let me just call that R sub X. And now what I want to do is convert that piece back into a Thevenin, so that I will be able to combine R sub 3 with the series voltage that will result from the Thevenin equivalent. Or I now keep this left piece and what's going to be the value of the source voltage now? I've now consolidated R1 and R2 into its parallel equivalent and called that R sub X. I now need to take the current that I originally had and multiply it by that resistance, or I now have V over R1 times R sub X. And maybe instead of continuing to carry all of that notation, let me call this I1, and well, I guess I'm getting ahead of myself. I now want to combine that. You guys didn't know we were doing calisthenics this morning, did you? We're going back and forth, back and forth. Now we want to convert this one back to a Norton so that it's now in parallel with what we originally wanted to have in parallel with that left-hand side. What do I end up with? I can do the left-hand side. That's just continuing to keep it as R sub B and I1. But now what do I have here? what's going to be that current source? Let's call it I sub 2. And what does I sub 2 actually equal? It's V over R, where in this case V is this mess, V R sub x over R1, divided by the R, which is now R sub y. Or I sub 2 is now the V over R sub y and now what do I want to do? Now I have two Nortons in parallel. I should be able to just combine those. I have the two I sources, I1 plus I2, and the resistors just become parallel combinations. So that I now have I1 plus I2 and what is this resistor? This is now R sub B in parallel with R sub Y. And if I wanted to find I load out of all of this for different values of R sub L, now I just have to compute I1 plus I2 and keep that together. I need to find R sub B and make that in parallel with R sub L. And now what's the formula for I sub L? This could be on tomorrow's test. This particular step in this problem. Find I sub L from this circuit. That's the current divider. We now have some fraction of the total current going through R sub L. And that's now just the other resistor over the sum of the resistors. Did you at least follow that last step? And after the exam, you can go back and figure out what in the world was he doing. But really, we were just doing different equivalences. We were transforming or doing source conversions, going from Thevenins to Nortons to Thevenins, trying to eventually end up with two Nortons in parallel, and then we can combine sources from that. Now, if you weren't strapped in before, now we really need to be strapped in. Let's do all of this together. So now we have different pieces and parts. We have source transformations, source combinations, and source splitting, and now we're going to try to do all of that to simplify this circuit. And this particular circuit is a problem in Chapter 4, and in particular, problem 67. We have two sources. One's an independent current source, one's an independent voltage source, and some resistors interconnected. Do you see that we sort of have something that we just talked about? If this was just a series connection across that, then we could start splitting our source, voltage source of 300. Meaning, let's now convert this Norton into a Thevenin. And what will that look like? If I convert a Norton into a Thevenin, what do I have? I'm going from parallel, a current source in parallel with a resistor. I'm converting that into a voltage source in series with a resistor. What will that look like? That's the structure. Now I have to assign values to those pieces. And what kind of a source do I have now? Current or voltage? Voltage. And where is the polarity sign, the positive polarity sign on that voltage source? On the right or on the left? Needs to be consistent with the direction of the current in the current source. I now have this. Whoa. And what's my resistor value? It stays the same. What's the value of that voltage source? IR, isn't it? Which is now 3 times 150, or 450 volts. Now what I want to do is play on that node. That node is always going to be fixed at 300 volts in the bottom piece and in the top piece. Let me pull it apart or split it and see what I get. So now if I split that, on the left I have the 300 volts, and that's now in series with this 150 and 450. And I keep what I had before, the 300, and this is now the 40, the 8, and the 10. What can I do now? Oh, question. So why can I split the voltage source? So why did I not want to do it in the first step? What I wanted to do in the first step was actually convert this parallel combination of current source and resistor into just one series connection. So I'm trying to, that yellow highlight, I'm trying to just make one series connection from the right side of my circuit to the left side. I'm trying to get rid of those two pieces in a sense and put them into a series connection connecting the 300 to the right hand side. I could have split up the 300, but then I have a 300 in series with a current source, and that's kind of ugly. So now what I want to do is I want to eventually combine these sources. Now I have two voltage sources in series. I can combine those. And I can retain the resistor. Or now I can, what do I end up with? What's my voltage source over here? Or do I want to label the polarity differently? If I combine 300 and 450 with the appropriate algebra on the polarity symbols, how do I want to combine those? I'm going to have, those are opposing each other, are they not? I have a net 150 because they're going against each other, and which one's more powerful? The negative is bigger, so now I can change this to minus plus 150, and I still have that 150 ohm resistor. And I'm keeping the bottom circuit for now. What can I do now? Do you see now I'm sort of back to where I was in the previous example? Now if I could make the voltage source on the left into a current source in parallel with a resistor and start to make that inner Thevenin source into a Norton, I can convert this one and I can convert this one, and that they're going to eventually be in parallel. Or what's the left one look like? What's the value of this current source? V over R. So it's just 1. And I have it in parallel with 150. Now if I do the second yellow, what's its value? V over R, with V being 300 and R being the 40. And I still have this. Can I combine those? I now have 40 in parallel with 8. And that ends up being some not so clean number, but it's 6.67, 320 over 48. And I can now convert this back into a Thevenin. And what will that look like? Isn't that now I times R? I was the 300 over 40, which is actually 7.5. So let me write this as 7.5. 7.5 times the 6.67. And this is still connected over there. One more step, and then I'm going to be able to start combining sources. Keeping the one on the left, what's my current source? Isn't it V divided by R? And now that comes back to a nice number. That actually ends up being 3. If I combine these resistors, their effective parallel combination becomes 15. If I now combine those current sources, I have 1 down and 3 up. What does that give me? I algebraically combine 1 and 3. Which one's going where? 3 is bigger than 1, and 3 was going up. I have that, do I not? Can I now convert that into a Thevenin? What's the resistor value? 15. And what's my voltage? What's the polarity on my voltage? Positive on the top. And what's the value? I times R, which in this case is 2 times 15, or 30. I've now boiled or condensed this original circuit, wherever it was, right there, down to, if I now needed to connect something across AB, wouldn't it be easier to analyze it in this form versus the previous form? That was the whole point of doing that gymnastic exercise, going back and forth, splitting sources, combining, etc. That won't be on the test, but some of the steps will be. Yes?
In general, if we need like find, let's say the voltage between A and B, would it be more efficient in this case to use like node voltage analysis, or to use this method?
So the question was, which analysis method should we use to find maybe the voltage across AB? I think it's going to really depend on what you feel comfortable doing. We're going to, after the exam, talk about other ways to find the Thevenin and Norton equivalents for given circuits that are to the left of terminals A and B. And we'll pick up at that point on Friday.